Hi there. My name is Leon Simons, and I'm here with Francisco Estrada from the National Autonomous University of Mexico at Ciudad de Mexico in Mexico City. Hi, Francisco.
Hi,
Would you
Leon.
please like to introduce yourself?
Yes, thank you. Well, I work at the National Autonomous University of Mexico. I'm also a visiting researcher at the Vrije Universiteit in Amsterdam. And here in Mexico, I'm the head of the climate change research program of the university.
Oh, great.
I used to be an economist, but now I'm not sure about that.
Okay, interesting. So you look at it from partially from an economic perspective, and also, of course, from a more physical perspective.
Exactly.
And that's what we'll be talking today. I think where those two fields meet. That's very interesting. And when we talked a bit before, you told me you studied in Amsterdam as well. Can you
Yes.
tell us a bit about that?
Yeah, well, I spent almost 5 years there. It was a very nice period of time. I really loved it there. And well, I had two supervisors, Richard Toll, which is he has been working forever in integrated assessment models, and also Pierre Perron, an econometrician that specializes on structural change and seeing when time series are beginning to act kind of weird. No, So it's very useful for climate change.
I can imagine. Yeah. So you did your PhD here.
Yes. Yes, on the economics of climate change, but a really broad spectrum. No?
Okay, interesting. Thank you. Yeah, I told you that I visited Mexico City myself when I traveled from Rio de Janeiro to Mexico City in 2009. It took me 4.5 months to travel there over land and water, and to see the tropical climate from up close. And yeah, I really like Mexico City. It's hard to imagine if you've never been into one of the mega cities of the world, but it's I think it's about 20 million people if you look at the suburbs as well.
Yeah, it's about 23 million people. And yeah, we have also altered the climate, the local climate, quite a bit with our urbanization. It's about 3 degrees more than it should be. No.
Yeah, that's a lot, and it's in a on a lake bed, right?
Yeah, exactly. Very convenient when it rains. It's very good for flooding, and
Yeah,
also for earthquakes. That's also a feature.
yeah, it's interesting how you can build one of the largest cities in the world on a lake bed.
Yes.
Yeah, great. Yeah, and today we will be talking about the risks of termination shock, and that's of course the as we talked about the shock of reducing either unintentional air pollution that can cause a termination shock. As we define it, it's about a 0.2 degrees Celsius of additional warming per decade, regionally or globally, especially globally, of course. And and you did also research on the impacts and intentional. It's called, as we call, sunlight reflection methods, SRM, geoengineering, and what I think. Yeah, maybe you have a presentation. Maybe we can share. We can show it, and then we can go through. You can go through it. If I have some questions about it, I will ask. But let me put it up. Where is it? If you can switch your screen to there.
Okay.
Like to have a hyperloop.
There?
Yeah, there we are.
Okay. Well, first of all, thank you for having me on. I'm a fan of the show, so it's very good to be here with you. And well, the thing is that we have been changing climate for a long time. I mean, at least since pre-industrial times, we have been putting greenhouse gases in the atmosphere and aerosols and a lot of other factors that may change climate. And actually, we have like very convincing proof that we have already changed in a very significant way climate. No, there is no room for skeptics now. No, and I mean, independent methods have been used to verify this. For example, here you have the preferred method of the IPCC using the latest or the most complete physical climate models. So one thing that we have learned from these physical models is that if you want to reproduce global temperature, here represented in the black line, you have to use, there is no other way to reproduce this since the 1950s. There is no way to reproduce this if you don't include human factors. No? So from the physical side, from the physical modeling side, we know that this is the only way. If you only consider natural sources, you would have stayed around zero, no, temperature change. And well, this is not the only way of testing this. In a paper we published in 2013, we used econometrics and statistical time series methods to analyze the radiative forcing that we can kind of understand, like the influence we have on climate. How much are we taking the planet away from the energy balance? No? So positive numbers indicate that you are going to warm the planet, and negative values say that you are going to cool the planet. No? So what we did here is to analyze different forcing variables. For example, the radiative forcing from greenhouse gases that you can see here, and then various components like including solar radiation and all the other radiative forcing factors. And then what we found is, well, if you start looking for structural changes, you have two very big changes in I don't know, from 1880 until the 2010s. No, for example, the first one, you have a very significant change in the rate of growth of radiative forcing happening around 1960. No, and this we could trace down to the end of the Second World War. No, when you have the population starts growing, the economy starts growing, and everything is dependent on GHG emissions. So you can see here how it changes. No, so
Yeah.
yes, and this is, well, we say that this is the onset of the climate change that really worries us right now. No? And then you have another change. I'm going to talk about this in more detail in the next slide, but around the 1990s, at the end of the 1990s, no, where the rate decreased a bit. And when you compare this to global temperatures, global and hemispheric temperatures, you can see that if you don't take into account variability, the signal is very noisy, no? But if you, for example, subtract the influence of the Atlantic the Atlantic multi-decadal oscillation, sorry, you can see that the radiative forcing becomes some kind of a moving average of temperatures. No? And we did this, we developed some statistical tests to show that these breaks are present both in radiative forcing series and temperature series. We developed co-breaking tests to really have proof of this. This is really a common characteristic between this time series. And we also use this test of testing if the trend, the underlying trend, is the same in global temperatures and in radiative forcing. And we had very convincing statistical results about this. But then we found some things that I think are quite amazing, no? Quite interesting. There were some other changes in the rate of increase in temperatures that we could link to very specific socioeconomic events that happened during the past century. And I mean, for us, it was really surprising to see such an influence, such a big influence of these individual events. No? For example, you can trace to global temperatures the effects of the two world wars and the Great Depression. There is a slight change in the rate of warming in global temperatures. And then one of the most interesting things is that around the 1990s, we had like a slowdown in the warming. We kept on warming, but at a much slower rate. And then
temporarily.
Sorry?
Temporarily,
yes. Now it's gone. No, and then what we studied, well, what could be behind this? No, so we applied these methods to the radiative forcing, for example, of CFCs, these compounds that were developed after the Second World War, and then starting having a huge impact on climate. And then we had this very successful international protocol, the Montreal Protocol, to control these substances. And it was really successful. Actually, I think it's the most successful international treaty we have had for climate change. No, even if it wasn't intended for climate change. No, so when this protocol started, we had a stabilization of some. For example, here is CFC 12. The impact on climate stabilized, and the CFC 11 actually went down. No, so you can actually see the impact of the Montreal Protocol in global temperatures.
And for the listeners who don't know, those regulations were introduced because the impact of these gases on breakdown of ozone in the stratosphere.
Yeah, exactly.
And but those trace gases, which are have never been there, those are completely artificial. Have never been on Earth before humans started making them. They have a very long atmospheric lifetime, and they, as you call it, as we call a radiative forcing, which is, as I always try to explain it, that what forces the climate to change. So it forces the climate with these greenhouse gases into a warmer state until a new balance is reached.
Yes, exactly. So it was very successful, and we kind of stopped this influence. No, we stabilized it.
The increase.
Yes, the increase, exactly. And then other thing that we can also see in global temperatures, this is kind of hair raising, no? Because the other thing we found out is that there is a significant impact of a change in the way rice was produced in China. No? At some point in the 1990s, they changed the use of water. They make it more efficient, and they changed the fertilizer. And these two things had an impact on a microbe that produces methane. So we had a stabilization, or what is called the methane pause. So the radiative forcing stabilized in the 1990s. So this also can be traced in global temperatures. We can see the impact of these changes in China in rice production. So this is the how much impact we have on climate. No? This is how the economy and humanity is really tied to the climate system. No? We're part of it. No?
It's interlinked. You cannot understand the climate without understanding what drives the changes, what humans do, what emissions are emitted, what policies are there, whether those policies are adhered to. Indeed.
Yeah, exactly. We're a completely coupled system. No? So yeah, this is something we might want to take into account. And then the other thing we found out here is that aerosols, tropospheric aerosols, had also a big impact. After the Second World War, we have this industrialization in Europe, the Marshall Plan to rebuild Europe, and then you can see it here. And then in the 1990s, we have this fast industrial growth in China and in India, and you can see how the aerosols helped cooling the planet, very quickly. So this is another thing we can see in global temperatures. And if you think a bit about it, it's all about us. I mean, this is something we produced. I remember in the 1990s and the following years, there were a lot of skeptics saying, this is proof since the global warming kind of stopped, not really, but kind of the rate slowed down. They were saying, this is proof that we don't have any impact on climate. And the truth is that it's the opposite. The decreasing warming was a product of specific human actions that you can go and see in literature, in history books.
Yeah.
And yes. And then, for example, if you take into account these three factors, you can analyze what happened with the radiative forcing. Here in blue, you have what actually happened, taking into account the Montreal Protocol, the changes in rice production, and the aerosols from China and India. This is what happened. The red one is if you take back, if the changes in methane due to changes in agricultural production in China wouldn't have happened, if the Montreal Protocol didn't happen, then you switch to the red line. And you switch to the green line if, on top of that, you didn't change the aerosols from the industrialization of China and India. And it's quite a big change. I mean, if you consider only the Montreal Protocol and the changes in agricultural production, is 0.25 watts per square meter. This is the amplitude of the solar cycle. I mean, from the minimum to the maximum, more or less. 15% of the total increase in total radiative forcing since, the 1800s. And it's about 1.1 degrees Celsius warmer. If this didn't happen, we would have been 1.1 Celsius warmer than in contrast. And if you take into account the indirect effects of aerosols, it's 0.34, much more than the amplitude of the solar cycle. So we have a huge impact.
Yep.
And then, as you were saying, Leon, this kind of good news of having slow down in the rate of warming, it's old news. It's gone now. It's completely gone. And
we unmasked it.
Yeah, exactly. And as you can explain much better than me, you can trace this to changes in the fuel ships are using, right?
Yes, and scrubbers. Indeed, yeah. So to summarize it, the small map shows global sulfur dioxide emissions, and it shows that over land, of course, there are a lot of emissions, but also between North America and China. So North America, including, of course, Mexico, and then also between North America and Europe, you see that there's a lot of shipping emitting also a lot of sulfur aerosols, sulfur dioxide, which turn into aerosols, and that caused temporary cooling over the past century. And we stopped doing that by about 80% starting 2020, with some regulations before that for more regional reductions. And indeed, that we see now that less sunlight is reflected back to space by this air pollution and the cloud formation, and more sunlight is absorbed, and especially the oceans over these latitudes are warming much faster than they would without this regulation.
Yeah, and this helps explaining like the really fast warming that we have been seeing in the last 10 years or so. No,
Yeah.
as Jim Hansen is now showing. No, I mean he's proposing that we are now in a very different rate of warming. No, a much higher rate of warming than we used to be. No, and yeah, this can be in part but because of the changes in relative forcing. But I mean, what worries me the most is this part of maybe the climate sensitivity is much higher than we previously thought. If that's the case, this is very bad news. No.
Yes, and I think I think for many people it doesn't really matter whether it's for an increase in forcing driving more feedbacks, or a relatively smaller increase in forcing driving even stronger feedbacks. The result is very much the same, of course. More rapid warming, leading to faster impacts which we have less time to adapt to.
Yeah, exactly. It's the time is running out, and as we all have seen from the international negotiations, we're not making much of this time we have. No, we're not really taking advantage of the years we have to adapt or to do something about it. And actually, well, we also did an analysis of global temperatures, and well, you can see it down here. I mean, first
Coming
you
a
have
bit bigger. I
yeah.
want to show your cat to get some more viewers, but
She's kind of shy. So first, for example, you had this really kind of moderate warming. Then you have a period starting around 1975 that it's much higher warming. I think it's 3 times the rate of warming, more or less. And since 2012, we have this much higher warming again. No, it goes from 1.8 degrees per century to 3.5 degrees per century, which is basically exactly what Professor Hansen has found. No, we use this statistical test to test if this change is part of the natural variability, of there is a real change in the trend, no, in the underlying trend. And in all cases, taking any of the time series you see here, from NASA, from the HAT crew, from NOAA, you have very significant changes. No, these changes are there. No, it's not an illusion, a visual illusion. No, it's there. No?
yeah, and I think I realized that if you just look at these lines, it's very hard to see the trend because there's all this variability,
Mm-hmm.
and eyeballing these lines, so just looking at a graph is not a great way of analyzing data, of course.
Yes.
And once you start really looking into the data, then you see that this trend is changing, especially if you understand the underlying drivers.
Yes. This is why we use this test. You don't impose the date of break in the slope of the trend. You estimate the trend, the break date. No, so
Yeah, based on the data.
yeah, exactly. No, and but as you can see, it's basically what James Hansen was proposing. It's off by 2 years, but it's basically the same thing. No.
Yeah, between 2010 and 2015, he shows both, and halfway is 2012.
Yes. No. So experience and statistical tests are more or less are highly correlated, and well, what we did here is something that you already did as well. Well, in 2025, we reached 1.46 increase in global temperatures with respect to pre-industrial values,
Yeah.
which this means that staying below 1.5 is dead. I mean, we're already there. I mean,
Yeah.
you cannot see the difference between 1.46 and 1.5. This is ludicrous to think that.
With variability, indeed, we are, for all intents and purposes, we are there.
Exactly. No? And if you assume that this trend is going to continue, then we're going to reach in 2040 around 2 degrees Celsius. And here you have a much more complete table that you produced. Maybe you want to explain this one?
Yeah, I think this is so this was from Grant Forster and Stefan Ramstorff. Let me pronounce it in German. Stefan Ramstorff. They made this table up to the crossing point of 1.5 degrees Celsius. And then someone on Climate Chat asked me when we would reach 2 degrees Celsius of warming if this trend, if this rate of warming continued. And this rate is based on natural variability corrected estimates of global temperature and therefore warming. Correcting for volcanoes, for the solar cycle, and for the El Nino southern oscillation. And then Foster and Ramstorff, they came to these estimates of the average warming rate of over 0.4 degrees Celsius. And then you can see from these different data sets at which point we would reach which level of warming. And as a subtext mentions, taken from their preprint, but the paper is based on the already published methodology. Yes, of course the rate of warming could decrease, but it could also increase further. So I think that's also important to always to point out that it is not a certainty, it is not a prediction, but it's a projection of what would happen if the variability corrected rate of warming continues over the next decades.
Yeah. So we are what we can say from this table and what we have been talking about. We're in a tight position, no? Because we already crossed the 1.5, and it's 2 degrees Celsius is going to happen in the next 10, 15 years, no?
Yeah.
And well, we keep failing in global negotiations. No, the climate policy at the global level, the mitigation is kind of, I don't want to be so negative, but it's kind of not delivering what we need. No, and also adaptation is also in the same spot. No, because we're not really having this significant funds to cover adaptation for a lot of people that are really going to suffer the impacts of climate change. No, so yeah, we're in a dire situation here. No, if you see, for example, this from the emissions gap report from last year, we are really not in any way getting near what we hope to achieve. No, the Paris Agreement is getting farther away from us as every day it happens. No.
Yeah.
No, and the radiative forcing, for example, we can see here the changes, for example, in radiative forcing from aerosols. This huge increase, no, and we also can see it, for example, in CO2. We actually the rate of increase in the forcing from CO2 has increased since the 2010s. No, we are now in a steeper with a steeper slope in CO2 increase. So this is a perfect recipe for start thinking of other types of I don't want to say solutions because there are not solutions,
Mhm.
but other measures. No, for example,
Yeah.
this solar radiation modification, no, in which you put some reflective aerosols in the stratosphere. For example, there are many other methods. This is actually called stratospheric aerosol injection.
I
And
cannot see the right slide. Is that me or?
no, it's going to come up.
Okay, sorry.
Yes. And you reflect, I think, like 1% of the incoming solar radiation, and then you can significantly cool the planet. No?
And that's 1 percentage point, right?
Yeah,
So an
exactly.
additional 1 percentage point, which if people don't know, that's yeah. So the sunlight coming in on average around the world is about 340 watts per square meter. So comes in, about 29% is now reflected, and increasing that by 1 percentage point means that it will be, instead of 29, it will be 30% again, because that's what it more or less used to be.
Yeah, exactly. And if you look, for example, at global temperatures, this is from a software we are developing. The reference here is to the previous software, where we haven't published this paper yet, but we are providing this very easy software that you can download and you can install in any computer, and it's going to emulate different GCMs, so you can play with it. And if you only look at global temperature, you see, well, instead of going, for example, with a huge increase in global temperatures that would take you more than 4 degrees by the end of the century, if you apply SRM, you would get this warming. No, so you will stay around 2 degrees Celsius. Of course, you can modify the amount of aerosols you inject into the stratosphere, and you can have more cooling or less cooling. But one of the things that I think it really matters is to understand that SRM is not going to take you back to the previous climate. No, it's not that you avoid climate change. What it's really going to happen is you're going to have a different type of climate change, but you're going to have climate change, and this becomes
Yeah.
apparent when you see, for example, the maps of warming. No? For example, if you see global temperature, mean annual temperatures, this is for 2100 without SRM in the RCP 8.5 scenario, and with
And before people start to hate the show,
yes,
it helps to understand what will happen in also in high emission scenarios. Again, that's not a prediction. That's just trying to understand how the climate changes with a certain amount of forcing. And some people really hate the higher emission scenarios, but I think many of them don't really understand why they are used. It's not that the world will warm that much, but it's trying to understand how it will change from different forcings. And maybe it's not 2100, but it could, of course, happen later. Thank you. Please continue.
yes, and also, yeah, I mean, if Professor Hansen is correct, and we have climate sensitivity of 4.8 instead of 3, then maybe you don't need this so high emissions to get to this warming. No, so
And yeah, indeed, with feedbacks, with warming feedbacks, but also, of course, as we are already starting to see in many ways, also carbon feedbacks, where certain regions, especially the boreal forest and the Amazon rainforest, are starting to turn into sinks, from sinks into sources of carbon. So then,
exactly.
indeed, with lower emissions of CO2, you could still reach high concentrations of CO2.
Yes. No. And then from a risk management perspective, it's a good idea to explore these high emission scenarios, even if we're not going to reach those levels of emissions, no?
Mhm.
Human anthropogenic emissions. No?
Yeah.
So you can immediately see the difference between temperatures with and without SRM. No,
Yeah.
I mean this is it appears to be a much easier place to live, no? If you applied SRM and you don't do mitigation, no?
Yeah.
Also, I mean, temperature is not the only thing. This is why I was telling that we are not going back to a previous climate. We're switching to a different climate. If you see, for example, what happens with precipitation, this is precipitation change for the RCP 8.5, and this is if you apply SRM to it. No? So, for example, you have a lot of regions in Africa and parts of Europe that are going to experience changes in precipitation, decreases in precipitation, quite significant, no, changes in precipitation. No? And this becomes even more clear if you estimate the date of exceedance, for example, of a reduction of at least 10% in precipitation. With the RCP 8.5, you can see here, for example, in these part of Mexico and, for example, Africa and these places, we already exceeded decreases of at least 10%. But if you apply the SRM, this is not going to change much, for example, for Mexico or for parts of Africa. But
Central America.
Exactly. No, here, maybe for the Amazons, it would be a good idea, but not for other parts of the world. For example, if you look at Africa, no, then you're going to reach much sooner these decreases in precipitation. No,
Yeah.
so this can have huge impacts on natural resources, on agriculture, on water availability, etc. No? And for some
Rate
other
of change.
sorry,
It's about the rate of change.
yes, exactly. No. And for other places, for example, Australia, well, maybe they would benefit, no? But I mean, this is why we started doing research on SRM, no? Because things are getting dire, as we were saying. I mean, we're not doing what we should do with mitigation. So someone at some point might say, for national security reasons, we need to do SRM. No, I can hear that maybe from my neighbor in the northern part of the world. No, and then we have to study what happens. What's the risk we're going to face if that really happens? No? So this is why we started looking at these things. And when we started looking at what could happen, for example, in the economy with SRM, I kind of got really worried, no? Because the papers that I have seen are very optimistic. No? So I wanted to really understand what was going on there. No? For example, this is a paper from 2020, and it's a very interesting paper. I really recommend if you have the time to read it. And what they said is, well, let's use this idealized climate scenarios. No, for example, the RCP 8.5, you have a warming that goes up to 3.6 degrees Celsius increase in global temperature. What happens if we use SRM and we keep the change at zero? No change in global temperatures. And this is kind of a very strange scenario. I don't know why they did this. But what happens if you have the RCP 8.5, but in reverse? I mean, instead of warming, you have cooling, but by the same exact amount and rate. So, and what happens with temperature? What happens with precipitation? No? And what happens with economic impacts? What happens with the economy? And this, for me, it's kind of strange. I don't think that a world that is 3.6 degrees cooler than today is going to be a richer world. No? We're going to be better off with minus 3.5 degrees. I don't think so. No, and well, you can see here that if we go to the RCP, we have RCP 8.5. The world loses just not that much, but it loses some GDP. No? But what is really interesting as well is that they went to what happens with the income projections and income distribution. And according to this paper, if you do geoengineering, then you get to a much a more equitable world. No, income inequality is seriously reduced with SRM, and that's something that really caught my attention. No, for example, if you see these Lorentz curves, I mean, inequality is higher in the RCP 8.5 than it is today. No, this is what represents today. Let's say 2010. No, and if you do geoengineering, you decrease in inequity in the world. No, so that's kind of strange. No, I mean, it would be. I mean, then the recommendation would be, yes, you should do SRM no matter what, because you would be even better than you are today. No.
Yeah, it looks like a big economic boom if you look at the bottom left graph. What is that? The GDP per capita is $1,000, so it's like $80,000 per capita increase if you see the extreme.
Exactly. No. So it's quite a bit, and if you
That's
go
global GDP, yeah.
Sorry, in this part.
No, bottom left C.
Bottom left, yes, exactly. No. So it's quite a bit, no. and if you have a cooling world, minus 3.6 degrees, then the global south is much better than if you stayed in current climate or whatever. And that's also something that really doesn't resonate with me. And this is something that Dan was talking about some shows ago, about integrated assessment models and economic models of climate change. That really, resonated with me, because it's exactly what I think. Most of the times, these models tell more about the limitations of the models themselves than what you can learn about what is going to happen in the future. No?
Yeah, tells you about the assumptions the person who made the models made are. I think that, right, it's like, okay, if Africa was only a bit colder, they would be much more productive.
Yeah, exactly. But
then feels like those lazy Africans, it's not, that's how I read it, right? They would be so much more productive if it wasn't that hot there.
But you also, yes.
And Indians as well, like India is like dark blue.
And Mexico and Latin America as well. So it's kind of, no. And I mean, for me as an economist, although I don't classify myself as an economist anymore, but it would be a very different world, because if the global north is having a rough time, I really doubt that the global south is going to have a good time. No, no, it's not going to work like that, at least in the near future. No, maybe we can reach another equilibrium down the road, many years from now. But
it's really strange. It's like because there's so many more people living in India, and then they will be more. Yeah, I don't know. I'd have to read the paper in more detail, but it says global GDP increases substantially due to rapid economic growth in warmer developing nations.
Exactly. No, if we go to this minus 3.6 degrees in global temperature, no. So I don't know, but that sounds like a catastrophe to me. But no, I don't know.
That's like halfway to the ice age, so that will be that will be quite an interesting planet to see from a scientific perspective. But I don't think that will be indeed. It's not. That's really difficult planet to model economically.
Exactly. No, and I don't think if now we had a younger Dryas, we would have a good time. I don't think that's the case. No, but Anyway, I mean, it's a very interesting paper, and it's one of the first papers that really tackles this thing. And I mean, I have a lot of respect for the authors. No, I'm not. No, and
it's not. Yeah, if we say something critical about it, it's about the output of the model, not necessarily about the the people who wrote the paper. They just presented what the model showed, of course, and it's always good to share what you find, even if it's if it's what do you call it? Yeah, counterintuitive, or often I think it also helps to raise some debate with these numbers, right? It's interesting to think about what would happen if you cool the planet, and where it might have some benefits and where it might not.
Yeah. And then, well, this gets us to the paper we're supposed to discuss today, like half an hour.
To introduce.
But then, why previous studies are so optimistic? Well, one of the things that we argue here is that we're not taking it into account the possibility of a disaster, a catastrophe. No, for example, and there is one catastrophe really associated to SRM, which is the termination shock. No, that at some point, for some reason, you have to stop this experiment, and then you're going to get the warming that you were masking with stratospheric aerosols. You're going to have it really quickly. I mean, in 5 or 8 years, you could have the full amount you were masking. You can have this full amount of warming in a very short time, and this could lead to any kind of future or any kind of geophysical tipping point. We don't know. No? We haven't seen that those kinds of changes. No?
Yeah, maybe we have, but we're starting to see it.
Not us. No.
Yeah, indeed. Like it depends how much you cool, and then how much. Yeah, if you would cool indeed these 3.5 degrees, we've not seen that. No.
Yeah, exactly. No. And the other thing is that it's not. I mean, the discussion about how SRM governance is related to greenhouse gas mitigation governance. How those two things are related? We think that it needed another look, no, and we needed to go a bit deeper with this, because at the end, if you talk to people in SRM, what they tell you is you have to do this risk assessment. No, for example, if you don't do anything, you're going to have a really risky future. For example, under the RCP 8.5. No, you can have geophysical tipping points. You can have catastrophes there. No, and then you need to compare this risk to the risk of SRM and see which one is lower. No, and they usually compare this to, if you have some kind of cancer, then you take chemotherapy, and that's kind of the idea. No, chemotherapy is kind of doing SRM, which I don't agree, because with chemotherapy you have the chance that you get cured. No, the cancer goes away.
But yeah, it depends. But you're right. Yeah, it's not a perfect analogy.
No, because
nothing is. But yeah, you're right. It's you could, yeah. There's many reasons why it's not perfect.
Yeah, no,
you don't cure it indeed, and it's one and what I think is nice about chemo is that we have many subjects, and even many were already critically ill, terminally ill. So it was, of course, not so risky to test on them. The biggest risk was that they would die, but they were already going to die. So then I think that's of course in a way a big advantage of the medical industry, that you have billions of test subjects for medication, and we only have one planet. So I think that's that's quite important, and that's also why we imagine how difficult it is to model a human body. But the planet is in many ways more complex.
Yes. And yes, and for example, there is no way that the problem we have with the excess of greenhouse gases we have in the atmosphere, that is not going to go away with SRM. No, you're going to mask it, but it's going to be there. No,
Yeah.
so you have to do mitigation as well. No, there is no. I mean, it's not going to save you. It's going to buy you some time. No.
Yeah, of course.
Yes.
I don't know anyone who advocates for SRM without advocating for mitigation. But it's indeed a good point, always to highlight.
Yes, and also because we have this part. No, for example, the problem of moral hazard. No, that since you start doing SRM, maybe you don't get the impacts you were going to get without SRM. No, the socioeconomic impacts or the impacts in nature. And then you say, well, it's not that important. We can keep doing SRM and postpone mitigation. No? So we have this this thing that can become a problem for doing mitigation in the short term. No, so
yeah, I think that's what our unintentional aerosols have already done.
Yes.
How many slides do you have left?
I'm going to go very quickly. No, not so many. How much time do we still have?
Yeah, like normally we try to keep it within an hour, but we never manage to do that. So
okay, well,
I'm okay, but Dan also has a question. But I think,
okay.
Please finish your presentation, and we can go through it maybe a bit quicker, indeed. And then if you have, we can always go back.
Okay. Yeah. Well, the thing is that what we did here is to include in the modeling the possibility of a catastrophic termination of SRM. No, why would that happen? I mean, there are many reasons why. No, you can have a war, you can have a nuclear war, you can have terrorism, you can have governance failure. It's not that easy to keep a thing so complicated as putting so many aerosols in the stratosphere for, I don't know, 100 years or decades, decades long. So
and even without wars, of course, people could realize or think without proper research being done that the risks are higher than the benefits and stop it. I think that was, maybe you'll get to that, but I think that was quite interesting that in the article covering your research on New Scientist, it said that even if there's a 10% probability per year, an annual 10% probability of the SRM, the sort of sunlight reflection method, stopping, that would over a century be result in a 99%. What was it, over a century? Yeah, a 99.9% chance of it happening. And I think that feels maybe a bit counterintuitive to most, but the data, like every year it's 10%, and of course that compounds then that increases the probability every year much more than it's just 10% every year.
Yeah, it's quite risky, no? And the thing is that if you're using SRM to mask a lot of warming and you have a termination shock, you're going to see rates of warming 10 or 20 times higher than what we have seen during the 20th century. No? So it's really high warming. And the problem here is what we call the governance paradox. No, the idea of using SRM comes from we have failed to do mitigation. No, but to safely deploy SRM and to manage this option, we really need to fix our problem of the governance of GHG mitigation. No, because at the end we are going to need to deal with greenhouse gases if we don't want to face a termination shock at some point. Huh?
Mm-hmm.
So the thing is that what we introduce is the socio-political geophysical tipping points, which basically is mitigation fails, people and the population gets really despaired because we're seeing impacts and nothing has happened, then your risk aversion gets overridden and you accept more risky options. You deploy SRM. If you have a governance failure, then you're going to have a termination shock, and then you're going to end up with geophysical catastrophes. No? So this is what we're saying in this paper, and what we did. This is I'm going to explain this really quickly. We have
don't leave people. We won't spend too much time on these equations.
Yeah, no, no. The thing
Please
is that
go through it and people can
Can go
skip
to-
it when they rewatch.
okay.
If they like, or can watch it in more carefully if they want to rewatch it and understand.
Okay, yeah, the thing, yes, people who are interested can see this in the paper, but the gist of this is that we have non-catastrophic damages, a probability that depends on the rate of warming that you are seeing of having catastrophic damages. No, this is basically what we're doing here, and we're adding persistence. This is something we have been discussing in climate economics, that the damages might not fade away really quickly. It's going to take time. And this is what you were saying. I mean, if we take into account that in every year you can have a termination shock and then you're going to recover the mass warming, you need to calculate the probability of that thing happening every year to be able to calculate the expected value of applying SRM, no, to see if it's convenient or not. And this is what you were saying. I mean, if the probability of failure that you have this termination shock is 1%
Per year.
per year, then at the end, in 1 century, you're going to have a 64% chance of having a termination shock. No, so it's quite large. No, and to keep a complicated process with a probability of failure lower than 1%, it's really complicated. So you need to have, I mean, for example, 0.5%, you would have a 40% chance in 100 years, and a rate of 1.1% per year probability of failure, you're going to end up having 10%. So it really.
So indeed, that's like a 1 in 1,000 chance per year results in a 1 in 10 chance over a century.
Yes, so you really have to have under control of this thing. So the idea here is we used different scenarios. No, one in which you successfully apply SRM and there is no termination shock, and one that mitigation fails and you don't do SRM, so you get to almost 5 degrees at the end of the century, and scenarios in between that depend on when you start doing mitigation. For example, if you start doing mitigation 10 years after you started doing SRM, you get to this line, and the difference between perfect mitigation, perfect SRM and early mitigation is only 0.4 degrees. So the gap is quite small. But if you don't do anything, the gap is really high. I mean, you're masking more than 2 degrees Celsius. So if you have a termination shock, it's going to be really bad. And these are the decision surfaces. I mean, everything that's below this black mesh makes SRM more dangerous than not doing anything, than staying with the RCP 8.5. No, so
red is in a way good.
Yeah, exactly. Red is good for SRM, and here you have the probability of failure and how quickly you do the phase out in case of failure. No, if it fails, you can let it rip, and then you're going to have the mass warming in, I don't know, 5 years or less, or you can do your best to kind of slow this process down, and maybe you can take for 20 years. No, but if you don't do mitigation, if mitigation fails, then you have a really tiny strip of possibilities of probability and transition years that are actually risk reducing for with SRM. No, the rest is really bad. And here it's something that is also counterintuitive. If you have a low probability, but it's not really zero, it is much more dangerous because failure is not going, it's likely not going to happen at the beginning of the period of the scenario of the century. No, it's going to happen maybe at the end, and the gap between SRM and without SRM, the gap in warming is going to be bigger, and you're going to get a huge termination shock and really bad damages. No, so in a sense, it's better if you have a larger probability of failure because it's going to fail earlier, and you're going to have a more manageable termination shock.
Interesting. Thanks.
And then, for example, if you do mitigation, then the red area, which is helps you to decrease risk, is much higher. No, but if you postpone mitigation 10 more years, this area where SRM is risk reducting is much lower. And if you wait for 30 years for starting mitigation, then you almost go back to no mitigation. No, it's very risky. And the other thing that we explored is in which cases it would be good to apply SRM. No, and I'm going to summarize this really quickly. And if you are looking for a small cooling with SRM and you're doing mitigation, you're going to be probably fine. But if you are trying to do a lot of cooling with SRM and you're not doing mitigation, about 95% of the area is going to be risk increasing, not risk reducing. So you would be better off without SRM. No? And well, I'm going to, and one other thing that it's really important, if you think that tipping points are more likely to occur even with lower degrees of warming, then it is not a good idea to do SRM. No? And we go back to the parallel. Sorry?
Can you repeat that last point?
Yes. If you think that you're going to reach tipping points for lower levels of warming and lower rates of warming, then it's not a good idea to do SRM, no? Because the area in which you're going to have benefits for SRM, it's really much lower than if you think that the climate system can take more warming and a rate of warming much higher, no?
That's really counterintuitive. I think the goal of SRM would be, one of the goals, of course, is to help to avoid tipping points.
Yes.
So if the tipping point threshold is low, for example, if it's 1.5 for coral reefs or for the AMOC or for the Greenland ice sheet or for the West Antarctic ice sheet, which it is, wouldn't that be more reason to do it?
Yes,
will that increase the benefit of doing it?
In one way, because the thing is that then you have to keep the probabilities of SRM failing very low, no?
Yep, exactly. Oh yeah, then
because
then it's more and more crucial. Now I get it. Now then it's more and more crucial to have a low probability. Otherwise, the impacts will be higher, because then you have all these tipping points being reached within a very short amount of time when the SRM fails.
Yeah, exactly. No, because the rate of warming would be really high. No, with if the SRM fails. No.
Yeah, and the chance of tipping points with this. Yeah.
Yes, and then we go back to the paradox. We're going to do SRM because we cannot fix the greenhouse gas mitigation. But if we cannot fix the greenhouse mitigation, it is not a good idea to do SRM, no? Because we really need robust mitigation for SRM to really work. We need to do mitigation. We need to ensure that the probability of failure is really low. And we need to have some things in place that if it happens, it's going to happen in a slow way. No, you're not going to recover the full warming that you were masking in a few years, you're going to spread this out in, I don't know, 20 years or so, no?
Yeah.
And then this is the last slide. The thing is that if the world is capable of doing safe long-term governance of SRM, this is likely a world that has already solved the mitigation problem. Thereby, you wouldn't need to have SRM, no, because you solved the problem, no. So this is kind of the I don't know if this is a summary of the paper. Let's say it like this. No.
Great. Yes. Thank you very much. Yeah, and as I responded to you, wait, let me remove that.
Yes.
Oh, Dan did it too.
Hi there.
Hi.
Hi, Dan. Thank you.
Hey, Francisco. Thanks so much.
Thank you.
I do have a number of questions for you, though. You said one of your assumptions was that when SRM fails, you get back to the same temperature. But we had Peter Irvine on the program about a year ago or so, and he talked about how cooling from SRM is a tremendous mitigation factor. In other words, CO2 causes warming, which causes more CO2, which causes more warming. But of course, the opposite is also true. That cooling reduces CO2, which causes more cooling, which causes less CO2. And in his study, he showed that SRM actually greatly reduces, not only overshoot, of course, because it reduces the temperature, but it reduces the mitigation you need to do to get back to whatever temperature you're trying to get to. So my question is, have you taken this into account? Because it's my understanding that if we do SRM and it fails, we don't get back to the temperature we would have gotten back to. We get back to a lower temperature.
Yes, you're completely right. I mean, the thing is that, for example, in this paper, it's really stylized, no? The how temperature would change back to the original level that you had. It is not like that. It is, but it's still the rate of warming. It's really high if you do that. Maybe you'd be, I don't know.
Great, but you don't go back to the same temperature.
No, but maybe the difference is.
It depends on mitigation. I think that's what you're saying, right? It just.
Well, let's assume the mitigation is the same for both, right? I mean, we have to make some assumptions. So I'm assuming that whatever mitigation we would have done, we're going to do with SRM and without. Okay, then we do SRM because things are getting really bad, and let's say we hold it to 2 degrees, or we hold it to even 1 degree, let's say, and of warming. But that's going to greatly reduce atmospheric CO2. In fact, if you look at Mount Pinatubo, the rate of increase in CO2 dropped in like half during Mount Pinatubo, which was a good proxy for SRM. And so it's my understanding that, again, you're going to have a very high rate of increase, but you won't go back to where you were in the same amount of time. I mean, of course, longer if you keep pumping out greenhouse gases, you'll eventually get to that, but that will be at sort of the normal time frames.
Yeah, so, exactly.
But you didn't take that into account in your study, did you?
No, but for example, if you look at not these simple projections of climate, but if you go to the GCMs, yes, you have lower warming, but not much lower warming. It's not going to be 0.5 degrees or 1 degree less of warming. No, you are going to still. I mean, if you're really masking 2 degrees Celsius, you're going to get, I don't know, 1.8, 1.7, something like this. And you can see this from reduced complexity models. For example, the model we use here is the Magic 6 model for doing this. But for example, we have this software that we are emulating real GCMs, and it's calibrated to get you the closest possible representation of these really complex GCMs. And yes, you might get a little less warming, but it's not like it's going to solve your mitigations problem.
Well, it doesn't solve it. No, it doesn't solve it, of course. If so, we should just do it anyway, I guess. Yes. But of course, if Jim Hansen's right, and Leon, and that climate sensitivity is really 4.5 degrees instead of IPCC's assumed 3 degrees, well, then this cooling mitigation effect is even larger. It's 50% larger, right? Because that means, it works both directions, right? Heating causes more heating, then cooling causes more cooling, and it lowers greenhouse gases. And okay, so anyway, that was one of my questions. And the other question is, you have a damage function, right?
Yes.
And you assume a certain amount of damage if you don't do SRM.
Yes.
And then you assume it drops if you do SRM, but then it shoots up even much higher if SRM fails. But doesn't your damage function max out at 3 or 4 degrees of warming? Like, isn't there a collapse of civilization, and then it doesn't really matter to go beyond that? Doesn't mean anything?
Well, it really matters. I mean, how can I put this?
Like, you can only die once, I guess, is another way of putting it.
Yes. If you lose 100% of GDP, you cannot lose anymore. No,
right.
That's yeah. But I mean, you have to get to 100% of GDP. You have to really do SRM in very, very, very bad way. No, I mean, no.
But we're expected to hit 4 degrees by the end of the century, roughly. I mean,
yes,
about that. And Kevin Anderson, you might know Kevin Anderson, climate scientist, out on the show a few times. He said 4 degrees is not compatible with an organized global community. And now, when he was on the show last time, he said maybe that's closer to 3 degrees based on what we know now. But so my point is that it's kind of like chemotherapy. Why do you do chemotherapy? Is a terrible thing to do. It gets you sick, you lose your hair, you get nauseous, almost kills you. Like, why would you ever do that? That sounds crazy. Oh, you're going to die if you don't do. Oh, okay, I'll take it right now. To me, SRM is something similar. It's like the damage of not doing it is so catastrophic.
Yes.
It's a different right now, shave off 0.1, okay, you can argue that, but we're talking about preventing 3.
What's your question then?
Let me just try to answer those questions because they're really interesting. One of the things we are doing there is not comparing, not looking at the damages of RCP 8.5 and then RCP 8.5 plus SRM. We're looking at the difference, no? We're looking at how this thing changes, no? So if it's really bad in both cases, it kind of compensates, no? It's one minus the other. And then this helps you to really get a better answer of the questions you're asking. And one of the things that we did in the paper, I couldn't show it here, is to really play with the parameters of the equation. We have no idea what would happen if we have a very rapid warming, no? As we don't have a very good idea of what would happen if we have 4 degrees of warming at the end of the century. Who knows? No, we have some kind of idea, more or less, no? But it's not something you can really pin down, no? So what we did is an extensive sensitive analysis. So you could see what happens if damages are much lower or damages are much higher. No, so you're comparing this difference. So you can get this idea. And what you were saying about the chemotherapy, yes, but I think there is a big difference. If you do chemotherapy, you have a slim chance, but you still have a slim chance of that thing saving your life, no? In the case of SRM,
more than a slim chance, I think. But
it can be very slim, but there is a chance. If you do SRM and if you don't do anything else, there is no chance it's going to save your life, your planet, let's say. No, it's not going.
I disagree. I mean, you said I thought looking at your paper, and I might have it wrong, that you were assuming something like a 10% chance of SRM failing was like too high, to have an overall benefit. But let's just pick 10% chance of failing.
No, it was 1%.
1% per year, right?
Yeah, 1% per year is 64%.
Let's pick 50% chance over a century. I'll whatever you want. If it's 50% chance of avoiding utter catastrophe and collapse of civilization, it might be worth taking that chance, especially since you now have time to get your shit together and to maybe do mitigation. I also don't agree with you. You said that mitigation, I mean, CO2 lasts in the atmosphere for hundreds of thousands of years. So if we just do mitigation alone, temperature never goes down, right? It only stops going up if you do perfect mitigation.
No, exactly. And one of the things...
So that's not quite there yet. We're not going to be okay. We'll still pass tipping points and all that kind of stuff.
One of the things that I really want to make clear is that we need to study SRM because we might really need it. And for example, let me tell you an anecdote here. For studying SRM here in Mexico, we have received a lot of criticism. Like, how are you studying this? You are going to enable this thing. And
right.
We have some newspapers here in Mexico who have criticized us for studying in a computer. It's not the real world. It's not going to...
just not even doing experiments, just in the computer.
Exactly. So,
okay.
So we're not against... We're not... Yes. I really, for example, I've seen Leon's position and James Hansen's position, and I completely agree. This is something we really have to study, and exactly because it's really risky, we really need to know what the risks are.
Yeah.
And I think this type of studies that, for example, what really kind of, I don't want to say it like this, but I'm going to say it anyway, kind of pisses me off is that, for example, the termination shock in previous paper was put under the rug. Like, we're not going to let this happen. This is not going to happen. Well, what if it does? I mean, as you were saying, we might have a catastrophe if we don't do SRM, but we also need to see what would happen if things go really bad with SRM. I mean, it's a risk management perspective.
Well, we're taking unacceptable risks. I mean, we're putting ourselves in this position. We're not really doing anything to solve climate on net, and we're going to end up in a very bad place. And it could be the least of the least worst of the bad options we have, right?
Yeah, at least we cannot take this off the table. I mean, we need every trick in the bag we have to see how things come up. I mean, if we keep postergating whatever the global mitigation of greenhouse gases for another 10 years.
Yeah,
postponing. Yes. So thank you, Leo. We're going to be in a world that no one of us want to live there. What we were discussing, if we are going to breach 2 degrees Celsius in the next 10, 15 years, God, no.
Mm-hmm. I think your point that that you're being shunned, or that you're getting backlash for doing research to reduce risks. It's quite crazy, of course we've been experiencing that for the past 5 years. Well, just doing research on the impact of our unintended aerosols, right? And then I can imagine, even if you do research on intended aerosols and what the potential impacts thereof are, I can imagine you get back a lot of pushback. But I think if people just think about it a few more seconds, like, you don't want research, you don't want to avoid risk, you don't want to know what the risks are of doing it versus not doing it, because otherwise it just sounds like a good idea that we should do if you don't do the research of the potential risks, right? For many stakeholders, and then you could indeed have the wrong, all the side effects which you don't want happen because uninformed decisions are taken.
Exactly, and the problem is that these are the first studies done in Mexico about SRM, so we are getting a lot of attention. And the thing is that what I really find that cannot be done in the 21st century is that you have topics that are taboo in science. You cannot go back to the 13th century and say, no, you cannot touch this with a 10-foot pole. That's completely the opposite.
I think it's very much about feelings, right? if you have two guys playing with balloons in Mexico, who emit about as much as a box of matches, and they get like global media attention. Even I think your article now.
Well, we had him on Climate Chat.
Sorry, yeah,
we had making sense.
It's like, to me, it's like even they themselves they say they're two guys playing with balloons, right? And it's, if you understand the orders of magnitude involved, we're talking about millions of tons of sulfur, and then they emit a few grams or a few kilograms, and then of course it's a media stunt, and that's what people I think most, of course, media, it's not a rational scientific undertaking, right? It's like, we know people will get emotionally involved if we say these two guys from the United States are polluting our atmosphere, and yeah, but it's I can imagine it hurts these kind of articles, and also what caused it does hurt your research in a way.
Okay. Yeah, and we should bring in Stacy now, and because we're hitting the time here, so let's bring in Stacy. And I know Eli has a question. So, hey, Stacy.
Oh. Hey, hi, Dan, Leon, and Francisco. Thank you for being here. I just wanted to, Dan, the program that Dan was referring to is solar-geoengineering, one balloon at a time. That was Luke Eisman who was on, and that was about 1.5 years ago. So you have to scroll down. And then if everyone could please like and subscribe, we don't say it often enough. And it really just helps the algorithm. You know, in addition, Francisco and I both have cats here. So we could use all the support we can get to get this message out to more people. And then something else I said last week, I will say it again. We are not SRM proponents, or we are not benefiting commercially from this. We don't want to do it. It is because we feel we are going to have no other options. So please don't think that we are shilling for something or someone or whatever. This is just because we aren't doing anything else. And it's the only thing we think that will be able to save lives. So there's that. And then my question is, and a lot of other people were talking about this, and apologies if you have explained this, but if you could put it as succinctly and simply as possible, the relationship between aerosols, CO2, and other greenhouse gases, how long SRM, and how we might stop or wean ourselves off of it.
Yeah, well, the thing is that, I mean, as we were discussing, SRM is about buying time, so we can have cheaper technology to do mitigation, and we can adapt. No, if we can increase our time for adaptation by 10 years, that would be fantastic. I mean, for example, here in Mexico, we just finished a lot of studies about what would happen to agriculture, what would happen in water, what happens to the economy, and it's really dire. I mean, for example, just let me give you one anecdote of this. If you consider the presidential term that we're having now, the next 6 years, the economic damages, with all the limitations we have for estimating these things, are equivalent in these 6 years to losing 25% of current GDP in Mexico. So this is the kind of thing we're looking at. I mean, no, so it's really huge. We have to do something, no? And mitigation is not happening. Adaptation is not happening at the rate we would like to see. So this interplay between aerosols, the time we can buy with this SRM, and with the necessary reductions of emissions to make it safe, it's something that we have to explore, and even talking from the global south perspective, no, it's really important because nobody, no country in the global south is going to do SRM. We have no capacity of putting that out, no. But for example, the US can do it, no, and they wouldn't have to justify it. This is not something that they have to negotiate. If they want to do it like that, they can do it. I mean, they can say, for national security reasons, we decided that climate change is unacceptable and it's a threat. And tomorrow we're going to put, I don't know how many.
5 megatons.
No, yes, and that's it. So we really need to be aware of the risks and benefits that could be implied by these types of actions. No?
Thanks.
Okay. Hey, why don't we go to Eli for his question? Eli, let's see if you're muted.
Hey there.
Okay. Hi there. We hear you.
Hey, thanks. I mean, you raised some very important points. I would like to emphasize the point that Dan made regarding warming causing more warming, and point out that if we did really robust SRM to counterbalance all of the radiative forcing, that would let us rebuild the polar ice caps, for example, and permafrost. And that in itself is part of the resilience that slows down the rate that termination shock comes back and affects things. I agree that fast termination shock would be particularly bad for ecosystems because if you really shock them hard, that's the hardest thing for them to respond to. But if we do robust SRM to really cool things off, the system itself builds in some of that resilience. And if along with that, we were also doing carbon dioxide removal, really pairing them, they're like two wheels of a bicycle. That puts us on a much better trajectory, even with possible interruptions of SRM than the one that we are on now. And I'd also like to add to the understanding of resilience, not as you were just suggesting, not envisaging a world of consensus and robust international cooperation, because I think that's a fantasy. It's never better than anemic, and that's the kind description. So you've pointed out some important risks, but I'd like you to consider this scenario of a robust strategy that really could work.
Well, I think that's what Francisco was actually suggesting, right? To do it all, to do serious mitigation and
adaptation.
Yes, and adaptation, that's very important. And one thing that I wanted to point out there is that, yes, SRM can buy us time, but there is one thing that we need not to confuse. No, SRM is not going to take us to the previous climate we had. We're going to have a climate change, but a different type of climate change. No, for example, right. Precipitation, as I was showing. For example, some regions are going to, or might experience, increased risk in decrease in precipitation. For example, heat waves. We have another project here in Mexico analyzing heat waves, and yeah, the temperature goes down, but at the same time, you have some places where relative humidity is going up. So the total effect of heat, it's not necessarily. And as Dan was pointing out in a previous episode, you also have the problem of ocean acidification. You have many other things going on that you have to take into account. It's not like you kind of erase all the problems of climate change. You are facing a new type of climate change. No?
Let me throw in one more philosophical issue, though. Your measurement is GDP, and your assumption is that increased GDP is good. But of course, GDP is driving destruction of the world, right? And if you listen to William Rees, who we had on the program long ago, GDP is this thing that we're all striving to increase means that we're consuming more per person, right? That's essentially what that means. And even putting climate aside, that causes, ecological destruction. So perhaps GDP is not the right measurement to use.
Well, it really,
happiness might be a better one, but
I agree with you, but I mean, from the perspective of the global south, yes, it really depends where in the world you're at. No,
yeah, it's true. It also,
because for example,
if your GDP is extremely low, like in global south, then
here in Mexico, we have the previous president was saying we have to move away from GDP and talk about happiness, and that was something that it has the wrong political intentions. Don't judge me because my economy really sucks, but we're more happy.
Well, but that's a longer term thing. So, hey, Stacy, do you have a few questions?
I do. I have some good ones.
If Francisco still has time, I don't want to. It's already 1.5 hours. Just to.
Oh,
yes,
it's up to you.
Just a couple of them.
Okay. So the one, if we stop burning fossil fuels, is there termination shock in that? Or I guess we would never do it quickly enough to create that.
Well, I'm happy you asked this because I didn't put it in the presentation, but I was going to. We have a paper. You know this, what we were discussing of the hiatus in warming, no? The slowdown in the rate of warming. We had another paper where we analyze what happened in the map, no? How this hiatus expressed around the world. And what we found out is that in the literature, they were discussing a thing called WACE, which is warm Arctic cold continents. No? So, and we found out that this, what we propose, is not necessarily right, is that we contributed to this thing because the hiatus didn't express in the Arctic, but it did in the surrounding areas. No, so you are decreasing the thermal contrast between these two areas. No, and what happened then is that you have the polar. I don't remember in English.
Vortex.
Yeah, exactly. But the jet stream, the polar jet stream, it's getting weaker, and then you have more waves in this thing, and then we have this huge these episodes of having this really cold polar air masses getting down to latitudes where they usually don't. No, so it really depends how you what you really mean with termination shock. But these kind of things, I think it's quite interesting because we are messing with the climate system, and the climate system is already altered. And even if we do the right thing of lowering emissions, we might get some surprises.
Oh, that's for sure.
Yeah. Also along those lines, in terms of variability that can affect it, old Jack Wolf said a stratospheric volcano eruption when SRM is being deployed can throw a big monkey wrench into the plans. And I feel like I know that one, that this SAI only lasts about 6 months. So it wouldn't be, we could always adjust. Is that the case?
Yeah, I think that wouldn't be a serious problem. Probably Leon or Dan have a better answer than me, but
no, I think it is a risk, of course. I think one of the biggest risks, natural risks to human civilization, is a supervolcano, and but then you're really talking about tens of millions of tons of aerosols, or even more, hundreds of millions of tons of aerosols into the stratosphere.
So and that's more than Pinatubo?
Yeah, much more. In Pinatubo wasn't a super volcano. That was just.
Well, if Yellowstone goes, that's the end of the U.S.
Yeah,
right
like Yellowstone, that would really could cause billions of deaths, because it would really impact global food production, and we don't have years of global food stocks. So and to me, that would be one of the reasons why we might also think about cleaning up the stratosphere. Of course, we don't even have we don't really have the technology to put a lot of stuff into the stratosphere. We don't even have the technology to do a lot of measurements of the composition of the stratosphere, let alone that we know how to clean it up. But yeah, that would be, to me, that would be one reason to think about that as well.
Well, this is
Leon,
why space-based SRM, you can modify that really dynamically, would be the best way of avoiding problems due to volcanic eruptions.
Yeah.
Leon, you had a final question, I think?
That he wants a gigawatt of solar AI into the stratosphere, in space in 5 years every year, but that's a different subject. I just want to think about a bit with you, Francisco, before I say bye, about this unintentional termination shock, and your point that we need a stable government for mitigation, and we need, of course, a stable government, global government, or some structure for SRM. But in a way, we have not a stable, the only place where we have it is in a way for international shipping, and for where we have really these global policies, International Maritime Organization working together to have from one day to the next this clean air regulation implemented. And to me, that's almost very almost contradictory to your point, where we can do this. We for greenhouse gas emissions, it's really hard, of course. It's much more harder than to do it for sulfur. But to do it on purpose, I think that wouldn't we need it even more organized and more rational government for that?
And we need decision makers to have the support of scientists, because they are looking at this problem and they want to solve this problem, but they don't realize that this is connected to another problem, which now we're discussing the problem with ships, no? But we're going to have similar problems in cities when you're going to decrease pollution, and then you're going to get more radiation, and then you're going to get more urban heat island effect, and then what are you going to do? Now, we need, for example, if you are decreasing pollution in cities, you need maybe to increase the coverage of green areas, no? Or to put
at least
to do some other type of geoengineering, like changing the albedo of the city and these kind of things, no?
And regional heat production. Indeed, I think that's a really good point. That we, of course, in Western Europe, we have also this termination shock in a way. If you use my definition of 0.2 degrees Celsius of additional warming per decade, that's what we've experienced, at least in summer, over the past 40 years, because of this reduction in air pollution. Do you look at that, for example, for Mexico City or for other large cities in Mexico, what that would look like if you start reducing air pollution, start cleaning up I don't know what the coal plants are doing now, if they are already desulfurized or not.
Well, actually, we just finished a 4-year project using a regional climate model to see how, local urban heat island effect and global climate change would affect the megalopolis of the Valley of Mexico. And it was very interesting because, for example, we were trying to see what happens if you increase the albedo of the city. No? And then you can lower temperatures about 2 degrees Celsius locally. No? That would be very beneficial for example, economic impacts, health impacts, and whatever. But what we realize is that another unintended consequences is that you would get you could get 40 to 60% less precipitation in the city because you're changing how things work. No, and that's the kind of thing we really need to pay attention, no, because I mean, no, having water is an important thing in a city like Mexico City, no?
But not too much. Yeah.
Well, it's
sorry,
really important, but
I forgot one thing. The extreme events would increase quite a bit. No?
Yeah.
One point, and this came out of an earlier discussion we had about SRM changing rainfall patterns, is that the rainfall patterns that we have now are not the rainfall patterns of a pre-industrial climate, right? These are the rainfall patterns which have been perturbed by all of the random, uncontrolled geoengineering that we've been doing. And I think a real solution is to have more development so that the world is not at the mercy of rain-fed agriculture. And that kind of development is good on a whole bunch of other bases, and then we can not be worried about having rainfall patterns that are more like pre-industrial rainfall patterns before we mess things up.
Okay. Yeah, but I mean, at least for the case of Mexico, I can tell you that, for example, changing from rain-fed maize production, for example, that would be almost impossible in the next, I don't know, 50 years maybe. And the other thing is that, for example, what we are seeing now in Mexico is that the northern part of the country is getting much less rain and it's getting more arid, no? And in general in Mexico, what we're also seeing is that we have maybe the amount of precipitation in total for the country is more or less the same. But what's happening is that you have a lot of longer periods without precipitation, and then you have extreme events, and then you have another long time of no precipitation. And this is a killer for water management. And if you want to do water management for agriculture, that already takes like 70% of the water in Mexico goes to agriculture. So it's going to be very, very complex. No?
I have one last simple question, and that is, we've talked a lot about GDP, and there has been mention of human lives, but that doesn't get as much billing. Is it because you're an economist? No one cares, or what would you say?
That's a very good question that I don't think we have a good answer for. No, GDP is something you can more or less measure, and you can get like more or less an idea of how things are going. But as I was telling you, other kind of measures like happiness can be used for political reasons that I don't know. We have to come up with something that it's much better than what we already have thought about. Happiness is not. I don't think it's a good proxy for GDP.
Well, lives would be a good one, though. You know, how many people die from climate change if you don't use SRM, and then obviously, and then you have to adjust for time too, because those people will be alive longer. And then if you fail on SRM, then there's a lot of death at that point.
But then you have to also to include people that have kind of a miserable life because they're just.
Well, no, I know. I agree with that. I mean,
that's nice. The nice thing with GDP that there's death inside as well, right? In theory, depends on how complex your model is. If you have less people, GDP goes down generally.
Yes.
So I want to, by the way, and thank you, Leon, for hosting today, and Francisco, thank you so much for joining us and sharing your research with us. I do want to repeat what Stacy said and like and subscribe so that we can reach more people with our programs, and that really helps. And I think we're going to actually do some more SRM discussions later in the month on February 22nd. We're going to have another show on SRM. So we're doing a lot this month on that. And thank you so much for your research. And it sounds like you're doing a lot of interesting things.
thanks a lot. And I'm very happy with this show, and I'm a avid viewer of your show.
Very
Thank
good.
you very much, Francisco. Please stay on. When we close the show, we'll speak later. Bye.
Yes.
Bye, everyone. We'll see you next time.
Ciao.
Bye.
Thanks. Bye.